Good morning, students. Last time you have studied pseudo unimolecular reactions, and the example of pseudo unimolecular reaction, it is the hydrolysis of methyl acetate in presence of acid. You know, when ester reacts with excess of H2O, that in presence of HCl, it produces acetic acid CH3 COOH plus CH3OH, and this phenomenon it is called as hydrolysis. And remember, hydrolysis phenomenon it is the reverse reaction of neutralization reaction. In case of neutralization reaction, acid reacts to form salt and water, while in case of hydrolysis reaction, salt and water reacts to form acidity and basicity. Here the hydrolysis of methyl acetate in presence of HCl, it produces acetic acid and CH3OH, that is the methyl alcohol. This reaction obeys first order rate equation, though it is bimolecular reaction, and this is due to the fact that water is present in a large excess, that its concentration remains practically constant. Again, the acid added does not enter into the products of the reaction and does not undergo change in concentration. And the rate of this reaction we can write dx by dt, it is equal to K into concentration of ester methyl acetate, that is CH3COOCH3. This reaction can be studied by removing known volumes of the reaction mixture from time to time and titrating with the standard alkali solution, and the final reading is taken after 24 hours or more. And I mean you have completed this practical. Still I will repeat how the progress of this reaction will be studied. In first bottle we take 5 ml of methyl acetate. Then this bottle is stopped, and we take precaution that this bottle must be dry and clean. In first bottle, that bottle is dry and clean. In that bottle we have taken 5 ml of methyl acetate, and in a second bottle you have to take 5 zero point 0.5 normal 100 ml of HCl solution. Then these two bottles are stopped and kept in a water bath, and here in a burette, you have to take zero point 0.1 normal NaOH solution. In a burette, you have to take zero point 0.1 normal NaOH solution, and that burette is filled taking usual precautions. That means there should not be air bubble in the jet part, and zero level of the burette it must be properly adjusted. Then the conical is taken, okay, and that conical it must be very clean, okay. Then the HCl solution it is poured into the methyl acetate solution, and immediately you have to pipette out 5 ml of the reaction mixture. Indicator is added, that is the phenolphthalein, and from the period you have to add NaOH solution, constantly steady flow with constant stirring, and the first reading it is your T0 reading, okay. Immediately as soon as you have poured HCl solution into the first bottle, immediately you have to pipette out 5 ml of the reaction mixture and adding indicator phenolphthalein, that mixture it is titrated with the enameled solution already that is filled in the burette. Okay, and that reading we call as T0 reading. That is the initial reading. And after time 10 minutes, the second reading is taken. Then at the intervals of 10 minutes, the reading of T10, T20, T30, T40, T50, such readings are taken and that readings are denoted as TT readings. That means reading at any time T. And T infinity it is provided by us. And for HCl solution, T infinity reading it is the 48.7. Okay, then the velocity constant K is given by all of you know here 2.303 divided by T into log of T infinity minus T0, that is the initial concentration A upon T infinity minus Tt, that is A upon A minus X. This is the hydrolysis of methyl acetate, and by putting the TT readings, okay, that means titration reading at T time 10, 20, 30, 40, 50, you can find the K values for different time. Okay. Then the second example here, inversion of cane sugar. Here inversion or hydrolysis of sucrose in presence of H plus ions as a catalyst can be represented as here the formula of sucrose C12H22O11 plus H2O in presence of H plus ions, it gives glucose and fructose. The rate of inversion depends on the concentration of sucrose because concentration of water remains practically constant and the concentration of H plus ions also remains constant as they do not used up in the process. And here the angle can be studied by measurement with the polarimeter, and all of you know the polarimeter it measures the angle of polarization. Okay, here sucrose rotates the plane polarized light to right and the resulting mixture is LIFO rotatory. Okay, this experiment it is meant for the second year B.Sc. So time being, simply remember that the inversion of cane sugar it is also a pseudo unimolecular reaction. Okay, these two examples are sufficient to write down the short note on pseudo unimolecular reaction. And here uh, alpha 0 it is the angle of rotation at the beginning and alpha t it is the angle of rotation after time t. And again 3-4 readings are taken and you have to calculate the k values by putting here alpha infinity reading, alpha 0 reading, then alpha t reading. Okay, and you will find the k values for the inversion of cane sugar. Then here by using this formula here k it is equal to 2.303 upon t into log to the base 10 alpha 0 minus alpha infinity upon alpha t into alpha infinity. By using this equation we can calculate the different k values. And the second point here it is second order reaction. After studying the first order reaction, then derivation of the velocity constant of first order reaction, examples of the first order reaction, then pseudo unimolecular reactions. Your next point it is the second order reaction here. In case of second order reactions, the rate or velocity is directly proportional to the square of the concentration of a reactant, or to the product of concentrations of two reactants. You know, the order of reaction, it depends on number of reactants whose concentration changes or determines the rate of reaction. Okay, and the reaction can be represented as follows. If we have two same reactants, then we can write the second order reaction as 2A, it gives product, or A plus A, it gives product, or A plus B. Here the two reactants are different. Okay, A plus B, they gives product. We can represent the second order reaction by these ways. Then the corresponding rate equations we can write. In case of this first reaction, we can write a rate, that is dx by dt. It is proportional to concentration of A and concentration square. That means here a rate of reaction, it is proportional to square of the concentration of the reactant. Then in case of second reaction, here rate, it is proportional to concentration of 2A. That means the product of concentration of the reactants. And here again the rate, it is proportional to concentration of A into concentration of B. Then the derivation of equation or expression for the velocity constant of second order reaction, where initial concentrations of reactants are equal or same. That means we consider the first case. We have two molecules with same concentration. So we consider here a second order reaction as 2A, it produces or it gives a product. Okay, then let the initial concentration of two reactants be the same, and we consider small a letter is the initial concentration of reactant, and the amount that reacted at each of the reactant in time t be x. Then the concentration of each reactant after time t is A minus x. See here, the concentration at the beginning or initial concentration we consider as A. This A is our initial concentration, and this X, it is our decrease in concentration in time t. Therefore, the concentration of each reactant after time t is the A minus x. Thus, the velocity of the reaction, it is given by dx by dt. It is proportional to A minus x bracket square. Okay, and this we can write as A minus dx by dt. It is equal to k into A minus x bracket square, and rearranging this we can write dx upon A minus x bracket square, it is equal to k into dt. And to find the value of k, we have to integrate this equation within proper limit. And integrating this equation, that means integration of dx upon A minus x bracket square, it is equal to integration of k into dt. Okay, so we can integrate this equation. See here, the integration of dx upon A minus x bracket square, it is equal to integration of k into dt. Therefore, the integration of this term, it is 1 upon A minus x, it is equal to kt plus c, where c is the integration constant, and when t it is equal to 0, x it is equal to 0, putting these values of t and x as a 0 in this equation, we get the value of c, and it becomes 1 upon a. Here when x it is 0, t it is 0, this term becomes 0, this is 0. So c it is equal to 1 upon a, and putting the value of c as a 1 upon a in the above equation, we get 1 upon A minus X, it is equal to Kt plus 1 upon A. Therefore, we write this right hand term towards the left hand. So, we can write 1 upon A minus X minus 1 upon A. It is equal to Kt. And simplifying this equation, we get A minus A plus X upon A in bracket A minus X. It is equal to Kt. And we can neglect, or we can cancel, this is positive A, this is negative A. Therefore, they cancel each other and we have X upon A in a bracket A minus X, it is equal to Kt. Therefore, the formula for K we can write as K, it is equal to 1 upon T into X upon A in a bracket A minus X. And this is the kinetic equation for second order reaction, in which initial concentrations of the reactants are equal. Okay. Remember, in this equation, K, it is the velocity constant of second order reaction. This T, it is the time. This X, it is the decrease in concentration. A, it is the initial concentration. Okay. And in this bracket, we have to put the values of A and X. Remember, A, it is the initial concentration. And then we can derive the derivation of equation for velocity constant of second order reaction, where initial concentrations of reactants are unequal or different. Okay, and for that purpose we can write the second order reaction as A plus B, it gives product. Okay, A plus B, it gives product. Then let we consider initial concentration of A as small a and initial concentration of B as small b, and the decrease in concentration as X. Then here, see the second order reactions or second order kinetics. A reaction will be of second order when the reaction rate would depend upon the product of two concentrations. The second order reactions are of two types. The rate is proportional to the square of the same reactant's concentration, and the rate is proportional to the product of the two reactant concentration. The rate is proportional to the square of same reactant's concentration. We have seen this. Here we considered A, it is the initial concentration, and X, it is the decrease in concentration. Therefore, for this reaction, we have written rate equation as dx by dt. It is equal to K in a bracket A minus X bracket square. And integrating this equation here, we have 1 upon A minus X, it is equal to Kt plus C, or here they have written Z as a integration constant. And when t it is equal to 0, x it is equal to 0, the integration constant, it becomes equal to 1 by A, and substituting these values we get 1 upon A minus X minus 1 upon A, it is equal to Kt, or K it is equal to X upon A T, okay, into A minus A in bracket A minus X. This is the kinetic equation of the second order reaction. Okay. Then the second case here. The rate is proportional to the product of two reactants concentration, and we have considered this A plus B, it gives product. It is our second order reaction where the initial concentrations are different, and if we consider small a letter is the initial concentration of this A reactant, and small b is the initial concentration of this B reactant, and decrease in concentration, it is the same for both the reactants. Then the concentration of this A and B at time t is the A minus x and B minus x. When the initial concentrations of the two substances participating are different, uh, then the rate is given by here dx by dt, it is equal to k in a bracket A minus x into B minus x. Okay, this is the rate expression when the two participating reactants are different, where x is the amount of any reactant transferred in time t, that is the decrease in concentration. Okay, then rearranging this equation, we can write dx upon A minus x into B minus x, it is equal to kt, and here the integrating this equation, we get 1 upon A minus B into 1 upon B minus x minus 1 upon A minus x into dx, it is equal to k into dt. Here, okay, on integrating we get 1 upon A minus B and integration of dx upon B minus x minus 1 upon EB, integration of dx upon A minus x, it is equal to k into integration of dt. Then here 1 upon A minus B, it is equal into minus ln B minus x plus ln A minus x, it is equal to kt plus z, that is the integration constant, and here we get 1 upon A minus B ln here A minus x upon B minus x, it is equal to kt. This is the final integration of this term. Remember, integration of dx upon A minus x into B minus x, it is equal to integration of k into dt. Simply remember this last term, 1 upon A minus B into ln A minus x upon B minus x, it is equal to kt plus z, that is the integration constant. And to find the value of integration constant, here we put t equal to 0 and x equal to 0, and we get the value of z, that is the integration constant, as 1 upon A minus B ln A by B, it is equal to z, that is the integration constant, and putting the value of z here, we get 1 upon A minus B ln A minus x upon B minus x minus 1 upon A minus B ln A by B, it is equal to kt, and simplifying this equation, we have k, it is equal to 1 upon t in a bracket A minus B ln B in a bracket A minus x upon A in a bracket B minus x, and changing this ln to the log to the base 10, we can write 2.303. Okay, here this equation, it is written for t, or for k we can write k, it is equal to 2.303 upon t in a bracket A minus B into log B in a bracket A minus x upon A in a bracket B minus x. Okay, we have to put here t and k here, or for time t we can calculate time values by putting k here. Okay, and this is the velocity constant of second order reaction where the initial concentrations are different. Remember, and the graphical representation by plotting the graph of log of b in a bracket A minus x upon A in a bracket B minus x, these values on y-axis and the time values on x-axis, we have a straight line graph. Okay, we have a straight line graph, and the slope here, it is the 2.303 upon k in a bracket a minus b. When we plot the graph of these values on y-axis and time values on x-axis, we get the slope equal to 2.303 upon k in a bracket a minus b, or k it is equal to here k is put here and slope is put here. Therefore, 2.303 upon slope into a minus b. By using this formula, we can find the k values also. Okay, and the examples of second order reaction. Here, the reaction between K2S2O8, that is the potassium persulfate and potassium iodide. This reaction is the second order reaction, and depending on the reaction progress, okay, you can learn the reaction progress by taking the K2S28 and Ki. I will explain you this practical tomorrow. Okay. So prepare well and get this integration well, or if you have doubts then you may ask me. So thanks for your patient listening.